Hello all, welcome to this lecture on Elements of Mechanical Engineering. We are in the first module where we are studying Basics of Thermodynamics. My name is Atchuta Ramacharyulu and I am working as an assistant professor in the Department of Mechanical Engineering. So in this lecture, we are going to see some numerical examples or problem solving on third law of thermodynamics. In the previous lectures, we have seen different laws which are related to thermodynamics. Now based on those laws, we are studying or practicing some numerical examples for each and every law of thermodynamics. Today we are going to see the third law of thermodynamic problems. So in this question, let us try to understand what is given in the question, and the question goes like, calculate the work done when 2 moles of an ideal gas expands reversibly and isothermally from a volume of 500 ml to a volume of 2 liters at 25 degrees centigrade and normal pressure. So in this question, the given data is 2 moles of an ideal gas is expanded reversibly and isothermally. We know what is isothermal process. It is a constant temperature process, and reversible process is nothing but it is the process in which the initial and final stage are equal. Okay. Now 2 moles of work is done on the ideal gas. Okay, so this is represented with small n. N is equal to 2 moles, and also initial volume is given in the question, that is Vi is equal to 500 ml, 500 milliliters, which is equal to 0.5 liters. So this is the initial volume where the ideal gas is expanded, and the final volume is 2 liters. Initially it is 0.5 liters. Now the volume of the gas is 2 liters. Okay. Vf representing the final volume, Vi representing the initial volume. Vi is equal to 0.5 and Vf is equal to 2 liters. Now the temperature given in the question is 25 degrees centigrade. So what is this temperature? This is the temperature of the gas, that is after expansion. Okay, T is nothing but T is equal to 25 degrees centigrade. After I converting this into kelvins, I have to add 273 to this 25, where I will get 298 Kelvin. Okay, now let us try to solve this question. So what we have to calculate? We have to calculate the work done on the system. So we have a system which is expanding the gas. So we have to calculate how much of work is done during this process. So work done, we have to calculate. So see here, this is the formula for calculating the work done for a gas cycle, for a reversible isothermal process. Okay, this is the formula for reversible cycle which is undergoing a isothermal reaction where the volume is expanding. Okay, whether the volume is expanding or compression, the formula is same. Depending on the values, we will get the required work done for the process. So here the formula is W is equal to, so that is work done is equal to minus 2.303. So this is a constant value which is taken for isothermal process, and this is multiplied by N, number of moles of gas present in the system, capital R, that is universal gas constant, and capital T is the temperature, multiplied by log V initial final volume divided by initial volume of the gas. Now using this formula we can simply calculate because we know all the values. So here minus 2.303 multiplied by number of moles is 2 and universal gas constant is 8.314 and the temperature is 298 Kelvin, which is given in the question, multiplied by logarithm log to the base 2 initial and final volumes. Final volume is 2 liters divided by initial volume is 0.5. So the final and the initial volume values are final volume is 2 and initial volume is 0.5. So no need to change the units of the volume values because they are anyway divided, and whatever the conversion will also gets cancelled. Now after calculating this value, we will get minus 6871 joules of work done. So this is the amount of work done when 2 moles of ideal gas, which is expanded isothermally from 500 ml to 2 liters of volume, where the temperature is 25 degrees centigrade. Okay, so this can be written in kilojoules also, simply minus 6.87 kilojoules of work is done. Okay, now, so this is the first question for this lecture, where we have calculated the work done, and the formula we have studied here is this one. This is the formula where this can be used only when the initial and final volumes are given along with temperature. Remaining values are all standard values like 2.303. It is for isothermal process. Capital R is nothing but the universal gas constant, and small n is given, temperature is given, final and initial volumes are also given. Okay, now we'll see the next question. So this is the second example, and the question goes like this. In a constant volume calorimeter, 3.5 grams of gas with molecular weight 28 was burnt in excess oxygen at 298 Kelvin. Here we have a calorimeter in which 3.5 grams of gas is burnt in excess oxygen. The molecular weight is 28. So this is M is equal to, molecular weight is nothing but M. Capital M is equal to 28, and the mass of the gas is M is equal to 3.5 grams. Okay, and the temperature is also given. Temperature initial is equal to 298 Kelvin. 298 Kelvin. Now the remaining part of the question is like, the temperature of the calorimeter was found to increase from 298 Kelvin to 298.45 Kelvins. Very small change in temperature. TF is equal to 298.45 Kelvin. So after that, the temperature has risen to a value of 0.45 increment. So TF is equal to 298.45. So this entire thing is done under a combustion process. Now, given that the calorimeter constant is 2.5 kilojoules per Kelvin. So this is calorimeter constant, that is K, small k is equal to 2.5 kilojoules per Kelvin. So what we have to calculate? So this is all the given data. We have to calculate the enthalpy of the combustion of the gas. So how much enthalpy is required for the combustion of the gas at this condition? So we have to calculate the enthalpy. Enthalpy has to be calculated. Now let us go into the question. See here, first of all we have to calculate heat evolved. So that is, heat evolved is equal to, so we are using a calorimeter, which is a closed container in which we are combusting, the combustion of the gas is being taken place. The weight of the gas is about 3.5 grams, and we are supplying some excess oxygen at the temperature of 298 Kelvin, where we are conducting this experiment. So first of all, we have to calculate how much amount of heat is developed inside the calorimeter. Okay, so the formula for this is K into delta T. Delta T is nothing but initial and final temperatures. K is nothing but the calorimeter constant, and the temperatures are initial and final temperatures, TF minus T initial. Because the combustion is happening, the temperature initially is very less when compared to the final temperature. Now, this K value is already given, the K value is nothing but 2.5 multiplied by final temperature 298.45 minus 298 kelvins. So this will be around 1.12. So this is kilojoules because this is heat evolved. So it is calculated to be 1.12 kilojoules. Okay. Now so this is the heat evolved for the given condition. Now we have not taken into consideration about how much weight of the gas is taken in the calorimeter. Now we have to consider that also. See here, heat evolved for 28 grams of gas. Okay, so this is the amount of heat that is evolved for. So this is the amount of gas that is evolved for 3.5 grams of gas. Okay, for 3.5 grams of gas, this is the heat required for combustion. Now we have to calculate the heat evolved for 28 grams. So 28 grams, that is 1 mole. So the molecular weight of the gas is given in the question, that is 28. So for 28 grams, that is 1 mole, we have to calculate that one. So for this, 1.12 multiplied by 28 divided by 3.5. So initially I have the value for 3.5 kelvins, 3.5 grams. Now here we are going to calculate the value for 28 grams. Here the final value is 9 kilojoules per mole. So this is the final answer. So it is the temperature, that is, it is the heat required for the combustion has to take place. Okay. So this is the enthalpy value that is required. So 9 kilojoules per mole is the enthalpy required for this reaction to be taken place. Okay. For the combustion has to take place, 9 kilojoules of enthalpy has to be supplied to the calorimeter. Now, so this is the question, second question we have completed, where we have to calculate the enthalpy. So the enthalpy has been calculated. Now we'll see the third example. Now in this question, the question goes like this. Calculate the entropy change in the system and surroundings and the total entropy change in the universe during a process in which 245 joules of heat flow out of the system at 77 degrees centigrade to the surroundings at 33 degrees centigrade. So there are multiple questions asked here. We have to calculate the entropy change in the system, surrounding and the universe during the process where 245 joules of heat flowing out of the system at a temperature of 77 degrees centigrade, where it can be converted into Kelvin. This is 350 Kelvin, and this is the temperature of the system, and the temperature of the surroundings is given like 33 degrees centigrade, where 273 plus 33 is equal to 306 Kelvin. So using these values, we have to calculate the entropy change in the system, surrounding and the universe. Okay, we have to calculate three values. Entropy change of the system, entropy change of the surroundings. By using these two values, we can simply calculate the entropy change in the universe. So these three things we have to calculate. Now we'll go into the question. So first of all, we will calculate the entropy change in the system. So delta S for the system is equal to Q, amount of heat supplied, divided by temperature of the system. So here Q is equal to minus 245 divided by 350. This is the system temperature. Just now we have written here, this is 350 temperature of the system, and Q is equal to 245 joules. Here, see carefully, 245 joules of heat flow out of the system. So it is taken as negative. See here, if I have a universe, in this I have a universe where I can consider a system. So this is the system. So the system has a temperature of 77 degrees centigrade. The surroundings have a temperature of 33 degrees centigrade. And 245 joules of heat is taken out of the system. 245 joules. So when we are studying the system, we have to give negative sign for the amount of heat being removed from the system. So that is minus 245. See here, minus 245 is indicating that the heat is removed from the system. So we are considering the system here. We are calculating the change of entropy for the system. So when we are studying the system, we have to see that the amount of heat removed from the system. So it is given negative sign. So in this question, minus 245 divided by 350. So this is equal to minus 0.7 joules per Kelvin. Joules per Kelvin. Here 245 are joules and 350 is in kelvins. Okay. And then we will calculate the change in entropy of the system. Sorry, the surroundings. For this, we will rewrite the formula. Delta surroundings is equal to Q divided by T surroundings. Now what is changed here? We have to write plus 245, not minus, because the heat is removed from the system and it is given to the surroundings. Now with respect to surroundings, the heat is added. So that is why we are taking a positive sign. So 245 divided by temperature of the surrounding, which is 306 Kelvin, and here we will get the value as 0.8 joules per Kelvin. So this is the value we will get finally. Now the third question asked is, we have to calculate the change in entropy of the system. Sorry, change in entropy of the universe. So this entire thing is called universe, where we have surroundings and system all combinedly called as universe. So delta universe is equal to delta S system plus delta S surroundings. So this is the system value is 0.7 plus the surrounding value is 0.8. Here observe carefully, we got negative value when we are calculating the change in entropy of the system, which is indicating the entropy is reducing. So minus 0.8 and entropy of the surroundings is 0.8. Finally, we will get 0.1 joules per Kelvin. So this is the change in entropy. Here this is positive sign only. Okay, here the change in entropy of the universe is equal to 0.1 joules per Kelvin. Okay, for 1 degree change in temperature, sorry, for 1 Kelvin change in temperature, 0.1 joules of reaction or heat transfer is taking place in the system. Okay, so this is the third example for this class. So in this we have calculated the entropy of the system, entropy of the surroundings and entropy of the universe. So all these three questions have been calculated. So here the change of entropy of the universe is 0.1 joules per Kelvin. This is the final answer. Now we'll see another example where the question goes like this. 30.4 kilojoules is required to melt 1 mole of sodium chloride. Here 1 mole is given. The content is sodium chloride. The entropy change during the melting is 28.4 joules per Kelvin per mole. Okay. This is the entropy required, entropy change while the melting process. Now we have to calculate the melting point of the sodium chloride. Okay, we have to calculate the melting point of the sodium chloride. Now I will remove all these things. Now first of all, what is the given data? The given data is 30.4 kilojoules. So this is the amount of heat required to melt 1 mole of sodium chloride. So this is taken as delta H. Okay, and delta S is also given. Change in entropy is 2. Sorry, this value could be wrong. 284.4 joules per Kelvin per mole. So this is the change in entropy while we are melting the sodium chloride. 1 mole of sodium chloride. Okay. Now what we have to calculate? We have to calculate the melting point. We have to calculate the temperature at which the sodium chloride is melted. Okay, we have to calculate the temperature. Now we'll see the so the question goes like this. So we have the very same formula for entropy where delta S is equal to change in heat transfer or enthalpy delta H divided by T. So this is TF, final temperature. Okay. Now the melting point can be calculated from this equation. TF is equal to delta H divided by delta S. Okay. See here, delta H is nothing but 30.4 kilojoules per mole. And the value of change in entropy is 28.4 joules per Kelvin into mole. So finally the answer we will get is 1070.4 Kelvin. All the units will be cancelled. Okay. Now the final temperature, that is the melting point of sodium chloride, is nothing but TF. This is TF value. So this is equal to 1070.4 Kelvin. Okay. And so this is the fourth example for this lecture, where we have calculated the temperature at which the sodium chloride will be melted. Okay. We have calculated the melting point of the sodium chloride where the change in entropy and heat transfer are given. Okay. Now we have a fifth example in this lecture. This is the last one. So here we are going to calculate. So first we will study the question. So you are given a normal boiling points and standard enthalpies of vaporization. Now we have to calculate the entropy of vaporization of liquids listed below. So there are some two liquids given here. First one is ethanol, where its boiling point is 78.4 degrees centigrade, and amount of heat required for this boiling is 42.4 kilojoules per mole. Similarly, second liquid is given, that is toluene. Boiling point is 110.6 degrees centigrade, and delta H is equal to 35.2. So this is the given data. The initial temperature, first of all we are calculating for ethanol. Ethanol is a chemical which is used in most of the industries. So where it is burned and some amount of energy is released from the ethanol. So this is the given data, like initial temperature or the boiling point is 78.4 degrees centigrade. So we will convert this 78.4 plus 273. This is equal to 351.4 Kelvin. Okay, 351.4 Kelvins. And after that, delta H. So this is the amount of heat required or amount of enthalpy supplied to the system for boiling. So delta H is equal to 42.4 kilojoules per mole. So here this is taken in positive sign because we have to supply some enthalpy to the system for combustion of the or boiling of the ethanol. Okay, so this is taken in positive sign only. Now what we have to calculate? We have to calculate the entropy. We have to calculate the entropy of vaporization. So for this, we will use the formula delta S is equal to, change in entropy is equal to delta H divided by temperature. So this is temperature. So that is boiling point temperature. So delta H divided by TB is equal to, so this goes like this, 42.4 divided by 351.4. So the change in entropy of this system is got to be 120.66 joules per Kelvin per mole. So delta S is the change in entropy of the system. A system which contains ethanol where it has a boiling point of 78.4 degrees centigrade and an amount of 42.4 kilojoules per mole is supplied. Now it requires, or it can create an entropy of this value, 120.66 joules per Kelvin mole. Okay, so in the given question there are 2 points. First one is for ethanol and second one is for toluene. So for toluene also we have to calculate in the same manner. Now we'll go for toluene. Here the temperature is TB. This is the boiling point temperature, which is given 110.6, where I will add this with the 273, where I will get the value 383.6 Kelvin. So this is the boiling point of toluene, and delta H, that is the enthalpy required for boiling of the toluene, is given in the question, that is 35.2 kilojoules per mole. Now I have to calculate the change in entropy. So that is delta H divided by TB. So this is equal to 35.2 kilojoules per mole, and delta temperature is 383.6 Kelvin. So finally what we get is delta S, that is the change in entropy of the system which contains toluene when it is boiled. The amount of entropy which we will be seen in the system is 91.76 joules per Kelvin per mole. Okay, this is Kelvin. K stands for Kelvin. So this is the amount of entropy that is observed when the system is undergoing a boiling point temperature. Okay. Now in the given question there are 2 questions asked, that is we have to calculate the entropy for ethanol and toluene. So we have calculated the values of this is for ethanol, and this is for toluene. So both the values are calculated separately. Now in the coming lectures, we are going to see some more examples related to the laws of thermodynamics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.